we're continuing our discussion of mirrors. And last class, we described what happens physically on a real basic physics level. What happens when electromagnetic waves hit mirrors? And we found that two things that happen. First is that because we know that the electric field needs to be perpendicular to a conducting surface, that creates a boundary condition for the electric field. And using that boundary condition, we could find what the nature is of that reflected field. So that was one way to look at it. And then there was another perfectly legitimate point of view that was, well, we look at the time-varying field, time-varying magnetic field, and that induces an EMF, and that EMF induces a current, and that current induces a electromagnetic wave. So in that case, you also get a reflected wave, except now you're including in the description of that wave something that's actually happening inside the material. And in many ways, that's probably a better description than that quite crude, the electric field needs to be perpendicular to the conductor, because even though that it is true and the argument works, there are cases where that kind of stops working really well, and then the version where we use the magnetic field actually works more reliable, and also describes, for instance, in ways in which this this mechanism doesn't work anymore. So, for instance, mirrors that are not good conductors are not good mirrors, right? So and that aspect is captured by the magnetic field description of a reflected wave, because you're including in the reflection this mechanism with which you're getting currents to flow in the middle. And if those currents are attenuated because it's a lossy material, then obviously the reflection is not going to be as good. Whereas if you use just the electric field being normal, you're completely missing that aspect. So it's just a slightly more advanced argument, but it's good that you know both sides of the coin. So finally, we found that the electromagnetic waves, when they're incident on a mirror surface, that when they're reflected, the angle with respect to the normal is flipped to the other side, and the incident angle is equal to the reflected angle. So that is something that is didn't take very long to come to that, but that's the central point that we will need to describe what happens when we start using mirrors in more optics experiments. So we'll start doing that today. So when we describe mirrors and optics, we usually don't do this from the point of view of there's an electric field component and there's a magnetic field component. We usually just say we draw this one ray, and this one ray is being emitted by something. So, for instance, it could be a light source, could be the sun reflecting off my forehead. It could be anything, right? And then that's you draw that as if there are electromagnetic waves pointing this way. Now, when we do that, we draw the direction of propagation. But it is important to remember that underneath the hood, electromagnetic waves are transverse waves. So they're transverse waves, which means that the electric and the magnetic field components are perpendicular to the direction of propagation. This was something that when people first started doing optics and try to make sense of optics, there was actually a big discussion about whether they should be transverse waves or longitudinal waves. So, example of a longitudinal wave, sound, right? So there, I'm speaking, so my vocal cords are creating waves, and these are acoustic waves, and they travel as density and pressure fluctuations towards you or around to the to the microphone. These are longitudinal waves, so the signal is encoded in something that is in the direction of the wave, whereas electromagnetic waves, transverse waves, the signal is perpendicular to the direction of propagation. Actually, so so that's the recipe for today. So we'll use that incident is equal to reflected angle, and then we'll start working with mirrors, and we'll see where we end up. Mirrors. This is our first entry into optics. So, like I was saying before, there's a shorthand of drawing that we will do, just like what we do when we do circuits. We don't really draw lines as finite metals and resistors as pieces of material that are resisting. But we draw the this reduced. We make these reduced drawings. So, for instance, let's say there's a ball here, and I'm standing here. So this is my eye, pupil, and I'm looking at the mirror. So the mirror, this side is reflective. Reflecting. That's why I'm drawing it that way. So we're not necessarily saying that the back couldn't be reflecting it as well. It's just that we don't care. Okay, so let's look at let's look at what happens when you look in a mirror. So let's say there's a ball there. Now you see the ball in the mirror, right? So what does that mean? Well, we assume that we're not doing this in the dark, right? Because if we're doing this in the dark, then that's cheating. That's like the trivial result. So there's some source of light. Let's say there's sunlight or something, and it's illuminating this ball. And let's assume that this light is nicely diffused. So we're in a room with lots of light sources. So there's light hitting this ball from all sides. And I don't want to talk about the way that lights will scatter off of the ball, but let's assume that there are also going to be light rays that are bouncing in all these directions, and that is the type of light ray that we will need to pick up in order to see. Okay, so what is the boundary condition at the mirror? It's this boundary condition at the mirror. And that is that theta I is equal to, oops, that's a Q, theta R. Theta I is equal to theta R. Okay, so let's follow one of these rays. So let's say this ray. So this ray goes like this. And now there, at the surface, there is a normal. And that's our normal. And this is theta I. And therefore, we have a theta R on the other side, which is about like this. So this ray of light goes in this direction, and that's the ray of light that's obviously not going to, we're not going to see because it's missing the eye. There could be somebody else there, but that's not important. So we have to find of all these rays the one that actually have that combination of theta I and theta R that are actually going to give us a ray that actually goes into our eye so we can actually see the ball. All right, so this one doesn't work, right? So theta I and theta R. This one doesn't work. So how do we find that? Well, there are two ways to do this. The first is just keep moving this point and keep drawing this until we find an angle where a point on the mirror where theta I is equal to theta R, and we will have a ray that joins the ball with our pupil, which is where our the light goes into our eye. Now that's a little bit it's a little bit too complicated. So there's another trick for it, and that's to do the following. So if you imagine that there's a theta I here and a theta R there, you can imagine that this ray is coming from the other side of the mirror. And we can do that because that angle works out exactly the same. That angle works out exactly the same. So instead of looking at the rays that are reflected from the ball through the mirror into the eye, we're actually going to reflect the ball on to the other side. So we're creating a copy of the ball, and the copy of the ball is going to end up at a distance, let's call it here. So that's 1, 2, 3, 4.5, 1, 2, 3, 4.5. Yeah, so let's call it here. Okay, so that's where the ball is appearing, and that is our ball prime. Okay, now, does it make sense to do that? Well, in fact, it's absolutely allowed, because if this mirror is doing its job, and we're assuming it's an ideal mirror, that means it's also that it's not dirty. It also means that it's not changing the color of whatever it is that you're looking at. And that means that if this mirror is 100% effective, you see the ball there as if it is there. So it makes perfect sense to say, okay, we don't actually see the ball here. We actually see it there, because that's what we see. Okay, so in that case, finding that ray is very straightforward, because now we have this particular ray of light, and this one hits our eye, and this one, upon reflection, happens to be coming from this point. And if we draw our normal here, then in this case, our theta I and our theta R are the same. So this is a clever construct, right? So if we want to see where the ball appears, we just put it on the other side, because that's actually where it appears. And then we just use the geometry to construct an image of the ball. So that's what you see. So the trick is you move your object to the other side of the mirror, and you just draw a ray from the mirror. Now, that becomes a little bit trickier when you have more than one mirror. So let's do more than one mirror here. So let's say I'm putting my eye here, and I'm putting the ball here, and I'm putting the mirror here. Oops, let me keep using this. And okay. Now the way we find it is we make a copy of the ball on the other side. Let's call it here, and then we draw our line. And where's my green? It doesn't look quite right. Hang on. Yeah, I don't know what I was doing. Hang on. This is actually here. Okay, so that's where our ball appears. This is our ball prime. This is the ball. And we see this one. And therefore, that one is from here. So we don't even need to draw the normal anymore. All right. Now, what happens with the second mirror? Well, this mirror will actually form an image of not just this ball, but also this ball. So we can put this ball over on this side. So that is, let's see, let's call it 4 centimeters. All right, so 4 centimeters on the other side is where we draw ball double prime. Okay, now how do we find the image? How do we find the ray that joins these? Well, it's a little bit more tricky. So we start out with this ray of light. And this ray of light is hitting the back of the eyeball. So we don't actually see this one, but stick with me. And then that one, upon reflection, appears to be coming from ball prime. So we're working backwards, just like what we were doing here, except we're having 2 mirrors. And then that ray is coming from here. So that's, if you had eyes in your back, like some teachers have, you would absolutely see the ball on that side. But that's not assumed that that's a thing. So then we obviously need a ball triple prime, and you could probably see what's happening. So we're going to measure the distance from here to there. So let's call it 6.8, and then that brings us to 12.8. Okay, so that's our ball triple prime. Okay, so let me draw a couple of lines here just to indicate how this distances relate. So this and this is the same, and then these are the same, and then finally, when we go from here to there, okay, that's anchored here, that's anchored there. So these distances are all the same. So hopefully you can reconstruct it. Okay, now this ray of light, this is ball triple prime. You actually do see it there, right? Because the mirrors are doing its thing. So we can draw a line from here to there. And then upon reflection, that actually appears to be coming from one reflection back. So it's actually coming from ball double prime. So let me draw the dashed line here. And then that is actually coming from ball single prime. And that is coming from the actual ball. All right. So that's what you see. You see a ball here, and you also see a ball there. Now we can keep going, right? We'll see a ball prime. We'll see a ball triple prime. We'll see a ball 5 primes off to the side, but I don't have that kind of space on the paper. Plus, I think that's making life a little bit more tedious than it needs to be. But the idea is that you'll see when you have 2 mirrors that are facing each other, and I'm sure you've experienced this in real life, you'll see copies of something and it will go forever. Now, of course, it's not in real life going to go on forever because mirrors are not 100% effective. So these balls will become increasingly dim and perhaps will have an increasing discoloration, but you'll see many, many copies of the same one. So that's the ray diagram for mirrors, flat mirrors. If we place the eye outside of this configuration of the 2 mirrors, you would still see the ball and you would see the reflections, except you would not see reflections beyond where the point of reflection has to be beyond this point. So you're going to see a limited number of copies. You won't see an infinite number of copies. So that's the that's with one eye. So let's see what happens with two eyes. So for instance, I have my eye here, and I have my eye there. And let's say I'm not looking at a ball, but I'm actually looking at myself. So I'm going to put my mirror here, and same thing here. Now this is the eye on the left, and is the eye on the right. Now the right eye would see the copy of the right eye here, right? But that's not what I want to pay attention to. I want to see, where does the right eye see the left eye? So let's look at that. So the right eye sees the left eye on the other side of the mirror. So that's, let's call it 3. So this is where left eye prime is. And that is the one that you see. So there you go. And you can see the eye, because the eye itself, it sparkles. It's got that twinkle. So that's where your right eye sees your left eye. And then now the same thing for the left eye. So the left eye sees the right eye. Let's do this in actual centimeters. So this is where the right eye prime is. So same thing, I'm drawing it slightly next to it. So that's this one. And that's this one. Okay, now, so your right eye sees your right eye sees your left eye here, and left eye sees your right eye here. So I hope you realize that this is a mirror image, right? Hence the name. This is a mirror image, because if to the right of this eye there is your right arm, and to the left of your left eye is your left arm, then you actually see this image of yourself mirrored. So you see the right eye on the other side. So you see this, the right side of your body in the opposite manner to how people see you. And this is something that is, I'm not sure if you've ever experienced this, but sometimes if you look at a picture, and I'm not talking about the non-flattering pictures, let's say best possible picture, you know, nice headshot, and you look at it and it doesn't look quite like the way it looks to you when you look in a mirror. That's why it is. You always see yourself in a mirror. I suppose there's a lesson in there somewhere. So we have 2 mirrors, one here and one there, and they are 90 degrees, form a 90-degree angle. And now if I place a ball here, so that's our ball, and we place our eye here, how do we see the ball double prime? So we want to involve both. We want to involve both mirrors. So the first one is here. So the ball prime is here. So let's call it 1.4. So this ends up here. So that's ball prime. And now this we extend so we can draw our image. And let's call this 2.8. Yeah, let's call it 2.8. So this is where our ball double prime ends up. So we see it here. That means that this light comes from here. This light comes from here. And this light comes from here. And that's how we see this. So this is this is known as a retroreflector. Retroreflectors, we see them a lot. The cool thing about a retroreflector is that no matter the angle with which you shine light at this retroreflector, it always comes back right at you. So you can do this experiment for yourself. So you can, for instance, place something here, and you'll see that one reflection, two reflections, is going to end up exactly on the opposite side. And if you put it here, it's going to be one, two reflections going to be on this side. So you point the light at the center, it's going to come right back to you. So these are used for reflectors in cars, right? So if you illuminate the back of a car with your headlights, the light always comes right back to you. And that's because they have a variation of this thing. And there also famously, there's a retroreflector that was left on the moon by one of the Apollo missions. And that means that when you point a laser beam at the moon, you gotta aim it a little bit. So you want to make sure that you hit the retroreflector. Then you can send a laser pulse and then measure how quickly it takes to get the pulse back. And you can figure out how far the moon is that way. So that's pretty cool. And then that means that all you need to do is aim the beam at the reflector. You don't actually need to move the reflector. It just needs to be pointing exactly in the just sort of towards Earth. And I believe there's a Big Bang Theory episodes where they do this. So retro reflectors. There's a homework problem that is using configuration of 3 of these. It's just a generalization of the one we just did. So let's talk about curved mirrors. So curved mirrors. Let's start with just an axis here, and then let's make it and draw this as a parabola. And the reflective side is here. Now, for curved mirrors, if you design them correctly, then this shape is a parabola. What it does is it will take all of the rays that are coming in parallel, so this one and this one, and I'm just drawing all of them. I mean, not all of them, just a bunch of them. And if you design this correctly, actually all of these, at the point where it meets the surface, there is a normal, right? And then there's an incident and a reflected angle. So here as well, normal, and here, normal, and here, normal. So all of these will be reflected in a different manner because the rays are all striking the surface at a different height, which means that at that time, this thing has curved more if you go down or less if you go up. And obviously the ray that goes like this comes straight back out. So let's see if I can get that drawn accurately this time. So this one goes like this. This one goes like this. This one goes like this. All right, and afterwards, obviously, they keep going, right? So goes out. And this point is the focal point. So we're going to indicate the focal point with F. So F is the focal point. Now, this is a I'm sorry. This is a concave mirror. We can also make convex mirrors, but I don't want to do that yet. But this mirror is it's already useful. So, for instance, if you look at a satellite dish, so satellite dishes have this shape. They're parabola, but they're not just a parabola in one direction. They're a parabola in all directions, so that's a paraboloid. These dishes are shaped in such a way such that when there's a satellite here and the satellite is emitting a TV signal, then all of that signal bounces off the mirror and goes to the point in the center. And the point in the center is where you would place your actual receiver. So the bigger the dish, the better the signal is that you're going to get, right? So bigger dishes are better. And you might not have noticed that these dishes are mirrors because usually they are they're coated with some kind of a paint, and that paint is actually transparent to the radio waves because they go through. And the reason you do that is you want to make sure that if by chance you have the sun pointing at this, you basically burn a hole in your receiver. So you want to make sure that you stop the optical light from getting reflected into the focal point, but you want to make sure that you do capture all of the satellite images, right? So application, satellite dish. All right. Now, what if we're not interested in using this as a satellite receiver, but we're interested in what happens when the rays of light that are hitting the dish are actually coming from a person. So, for instance, let's say I'm standing here. So now, again, we're going to assume that it's not dark out, so we can assume that there's going to be some light that's heading that's hitting let's say my forehead. Then there is light scattering off of my forehead in all directions, and we can construct the ray diagram using two specific rays as special cases. So the first one is a ray that is going like this. It is just like this one, except we are just picking only that one that is going parallel to this central axis of the problem. And because this is parallel, we're calling this the P ray. And just like all of these rays, because all parallel rays end up in the focal point, we can just draw the focal point here. So let's say drawing it here. So that means that this parallel ray goes through the focal point and does this. All right, so that one is just like what we were doing before. Now, the other ray that we're using is a ray that goes like this. So it's just another special one, and it actually hits the center of the problem. So this is therefore called the C ray. So it hits the center, which means that the angle of incidence is the angle of reflection, right? Because at this point, your mirror is perpendicular to the central axis in the problem. So that means that this ray does this. Okay, now this point, that's an important point. That's the point where our image forms. So this is where my head forms. So I'm gonna have to draw this. That's where the image forms. So the image forms here. The what do we mean by the image forms there? Well, so we picked the P ray and the C ray as special cases, but we should be confident in the fact that if this dish is designed properly, so there's a nice parabolic shape, that anything between the P ray and the C ray will also go to this same point. So what does that mean? Well, we can put, let's say, we can put a screen here, projection screen, so right here, and we could move this thing from closer to the mirror, further away from the mirror, and we'll see light. So we'll see the P rays and the C rays. But if you're here, for instance, you see the C ray ends up on this point of the screen, and P ray ends on this point of the screen. So we'll get light, except the problem is that it's not in focus. So go and now, because the P ray and the C ray are intersecting, this is where the image is in focus. So that's what we mean by the image forms here. That's actually shorthand for the image. Oops. Is in focus here. So that the only special, the only reason this is a special point is because that's where it is in focus. Okay, so let's see if we can calculate where that image forms. So let's call this thing the object. So that means that we're going to call this distance from the object. Didn't mean to objectify myself. We're going to call that d sub o, so the object, and we're going to call this one where the image forms the image. And we're going to call this height the height of the object, and we're going to call this height the height of the image. So there are two triangles that we can use to connect the HO and the HI with the DO and the DI. The first triangle is, and I'll try to see if I can. Yeah, it's getting a little bit cramped. But the first triangle is this one, and we're going to assume that the mirror is not curved too much. So we're going to assume that this is a right-handed triangle. So this triangle number one it looks like this. And this is DI. This is F. This is HO, and this is HI. And I hope that you see that that triangle fits here if we assume that this point is not too far. This point is not too far over to the left. Okay, so if this is a right angle triangle, then that means that HO over F is equal to HO plus HI over DI. That's the first triangle. Now this HI, I need to tell you that there is that there's a sign convention that we gotta factor in. But let's not worry about that for now. All right, the second triangle is formed by the C ray. So this is the object. This one is this one, so that's me. And then the C ray goes like that, so that's the C ray. And then there's an angle of incidence here, and then there's an angle of reflection. All right, and then here is where we have the other angles, right? So in that case, this is HO and this is DO. And this is HI and this is DI. And because these two triangles are similar, this is triangle number 2. Because these triangles are similar, we can describe HO over DO is HI over DI. Or in other words, HO over HI is DI over DO. Okay. Now we have 2 equations that relate HO, HI, DI, and DO. So let's take this equation and factor out our HO. So this is 1 over F equals 1 over DI plus HI over HO over DI. Okay. See if I did that right. Yeah, I divided out by HO. All right, now we're almost done. Our HI over HO, we have that over here, is DI over DO if we take the reverse. So then that means we get 1 over F equals 1 over DI plus sorry, HI over this thing is backwards. That's 1 over DO. Yes, 1 over DO. Okay, so so we're almost done. This is a the lens equation. Sorry, the mirror equation. And allows us to relate the image location and the object location through this this focal distance. Now, there are some things that are a little bit problematic in the way that I did this. So the first is that if we want to be consistent, we should say that if this one, if this HO is positive, then this HI, because it's on the opposite side, is negative. Okay, what happens if we do that? Well, that means that we change the sign here, and we would change the sign here, but we would also change the sign there and there. So we would still get the same equation, except we would get an inverted height. So we're going to call we're going to change the sign of HI, and we'll have the mirror equation, but we'll also have the magnification equation. So that's the how the heights are related. Hey, did I? Yeah, see, I have these reversed. That's DO over DI. Okay, so we're going to say that the HI over HO is minus DI over DO. And that is the magnification equation. So M is magnification. All right. So let's see how these equations work in practice. So let's say let's say I am not quite 2 meters tall, but let's call it 2 meters. And let's say if that's 2 meters, let's call the focal distance, let's call it 1 meter. And if that's 1 meter, let's call the distance, let me see, 1, 2, 3, let's call it 5. D of the object, let's call it 5 meters. All right, so what do we get for the image location? We use this one. We take our DI over to the left side, we bring the F over to the other side, and we invert it. So we get DI is equal to 1 over DO minus 1 over F to the power minus 1. Okay, that's 1/5 minus 1 inverted. Okay, that is 5/4 of a meter. Does that make sense? Yeah, that's not too bad. So if this is a meter, this is a little bit more, about 20% more. That's not too bad. Okay, so that's where the image forms. And now, how tall is it? Well, HI. Now that we have DI, HI is going to be minus DI over DO times HO. Okay, so DI over DO, that's minus 5/4 over DO. DO is 5 times HO, that's 2. All right, so 1 done, like a half. Yeah, minus 1/2. And this is in meters. Does that make sense? Yeah, that's not too bad. If this is 2 meters, this is about a quarter of it, so it's to scale. Okay, so how do we read this equation? Well, we read it as follows. We'll say because the height is negative, because the height is negative, this image is inverted. So HI is negative, image is inverted. Let's see what happens when we go to a mirror that has the opposite curvature. So rather than it curving like this, we're going to make it curve like that. Now the reflecting surface is still there. But in this case, when these light rays bounce off of the mirror, they actually are scattered in a diverging manner. I'll show you what I mean by that in a little bit. So this ray at this normal was going to come out like this. And this one is going to come out like this. This one's going to come out like this. Yeah. And they're all going to come from this point here that we're going to call the focal point. Except they're not actually coming from the focal point. You're actually they're being emitted as if they are coming from the focal point. And this is when we need to start talking about virtual versus real. Okay, so let's see what happens. So the rays, parallel rays, are reflected as if coming from F. Okay. So what does that mean for image formation? Well, let's do the same diagram. So we're going to take the mirror here, and let's do this. So let's call this F. 1, 2, 3, 4. Okay, I'm going to put myself here. So this is our object. This is our object distance. Hang on a second. This is DO. And now the focal point is not actually here. The focal point is here. But this is the F prime focal point that we probably don't need. Let's do the same thing we were doing before. So we have a P ray, and a P ray goes like this. And afterwards gets reflected and goes out like this. So this is our P ray. And our C ray does the same thing that we were doing before. And it's doing this. Now, when it's reflected, it is as if it is coming from a point on the other side. Same thing as this one. So that means that the image actually forms here. So the image forms here. Now, this is a concept which is a little annoying. It's just that this is how we talk about optics. So, what do we mean that the image forms there? Well, it means that because we can't put a plate here, right? There's no actual light here, right? Because all the light's been bouncing off the mirror. There's no actual light on this side, so we can't put a projection screen here. But what we can do is afterwards, with secondary optics, with eyes or whatever, we can look at the mirror and we'll see this person, me, will see the person standing here, and the person will be smaller. So the image actually forms on the retina or on the or the negative if you're taking an analog picture. So it's not really that the image forms there. It's just that the person appears to stand there, and that's where this person is in focus. So that's what we mean by the image is there. But because the image is on the other side of the mirror in this no man's land where there's no actual light, we'll actually call this a virtual image. So it's called a virtual image. We'll call this a virtual image. All right. Now, can we do what we did before? Can we use this to calculate the same mirror equation, but use the geometry on the other side of the mirror? And obviously we can. So we were using these two triangles and these two triangles, and in this case, we can do something similar. So we can put one triangle here, like this, and one triangle here. So it's showing up a little bit on the other side. So the C ray does this. This is the C ray, this is HO. And now on the other side, there is a triangle where this is HI, and this is DI, and this is DO. Okay, right? So this is triangle that sits here. This is the triangle that sits here. I hope you all see that. And we're going to use proper sign conventions. So we're going to say, because the image forms on the other side, we're going to call that a negative di. So we'll get HO over DO. The height is positive, so we don't have to worry about that anymore, but we're going to call this a negative image. So we're going to get HI over DI. Okay, so that's the first set of triangles. Now, second set of triangles. So first we were using these ones with the P ray. Can we find something similar here? Well, sure. There is, in fact, if you put the P ray here, this is F. This is F, like this. Yes, this is F. This is H I, and this is H O, and this is DI. Oops, that's DI. Now this second triangle is a little bit trickier because of all the inversions and the minuses. So first, let's look at this one. So it's HO over F is equal to HI over this distance. So it's HO over F is equal to HI over that distance. Now, this distance would be F minus DI. F minus DI, except DI, because it's on the other side, it forms on the other side, we're going to call that a positive distance. And the other thing we're doing is, because the focal point is on the other side of the lens, we're also going to call that a negative focal length. So we're changing the sign of the F's here. Okay, now, then what we do is we convert this into an equation that has only F's, DI's, and DO's. So we need to eliminate the HI's and the HO's. So the first thing we do is invert this. So we get minus F over HO is equal to minus F plus DI over HI. Then we bring the HI over to this side. So we get minus F HI over HO. And then we have here minus F plus DI. And now we are bringing in this one. So we're changing the sign. So we're going to get minus F becomes a plus F, and that's DI over DO. And now we have here the minus F here. So we're bringing the minus F over to the other side. That's DI. Okay, now we got to divide by a whole bunch of stuff. So we're going to divide by DI, F, and then we're done. So if we divide this by F and DI, we get that becomes positive. That becomes 1 over DI. This we divide by F DI, we have 1 over DO. And this we divide by 1 over F DI, we get 1 over F. And there we have the same equation. So this is, again, the mirror equation. It's the mirror equation. But DI is less than 0, and F is also less than 0.